Now let's look at stress versus strain. And specifically, we'll start off with a ductile material and look at mild steel. What you see on the screen is a tension sample or specimen that we would test in a lab. We would apply some hydraulic grips to the two fat ends and pull it apart while measuring the results of the test. So the sample is placed in the apparatus and the load is applied slowly. The machine is able to tell us what load is being applied, and we can measure the elongation over the gauge length. The gauge length is shown as L on the diagram. When we start to apply the load, it will elongate a distance delta. Recall the equation for stress, sigma equals P over A, and strain, delta over L, or the original length. We will use these formulae to calculate stress and strain for increasing load increments and plot them against each other to get the stress versus strain diagram or stress strain diagram. Let's talk about the stress strain diagram. The stress strain diagram is a fundamental description of the material capacity when loaded uniaxially. For this ductile material, a classic stress strain curve will have several distinct points and regions. The following properties are obtained from the stress strain diagram and are shown as we build it through incrementing loads. The first point of significance we get at the end of this linear elastic portion is the proportional limit. Beyond the proportional limit, stress is no longer proportional to strain, i.e. the linear portion of the curve is no longer followed. The yield point is the point where there are large increases in strain for little or no increases in stress, and can be seen here. Following the yield point, we get strain hardening, where once again we see increases in the material capacity as we continue to increase the load. We finally get to the ultimate stress. This is the maximum stress that a material can withstand. Following that, we fall off to the point of fracture. The fracture point. So this is the point of fracture. While it appears as if the load is dropped off, this is simply because we are using the original area for the calculation. As a result of Poisson's ratio, the area of the cross-section is actually reducing as the bar gets loaded. This is negligible for our purposes. If, however, we were to divide by the instantaneous area, we would get the true stress and strain, and it would plot as shown. So the modulus of elasticity. This is the slope of that linear portion of the stress strain diagram that we saw at the first stage, and is denoted by the letter E. This relationship is referred to as Hooke's law. Remember in the future that it only applies to the linear elastic region of the loading. Typical values for the modulus of elasticity vary from steel at 200 gigapascals, aluminum at around 70 gigapascals, concrete varies, classic concrete around 25 gigapascals, and wood in around 11 gigapascals. See the backleaf flyer of your textbook for a selection of values of E and other material properties that you may need to solve some of the problems that you will encounter. The stress strain curve can be broken down into these four regions of behavior. So a quick note on what we actually physically measure in the lab. How did we get the load? Is there some instrument that actually measures load? The reality is what we have is a calibrated piece of the instrument called a load cell, where we know the relationship between load and displacement. And what is actually being measured is the displacement. And then through that calibration, we are able to interpret that as load. Likewise, when it comes to the elongation, there are a number of ways that we can do this. We could do this with an extensometer, which measures, or the points of the extensometer move, and because of the geometry of the extensometer, we know the displacement. Quite often, too, we will use what we call a strain gauge. A foil strain gauge is applied to the surface of the material, and as it elongates, we measure the resistance through the gauge itself. And of course, as it elongates, the resistance goes up. So we're able, again, through a calibration, to understand what the strains are that are going on in the material, averaged over the length of the strain gauge itself. It is worth remembering that we can't actually directly measure stress or strain. Those are calculated from other observations. Here we will see the same test done for a brass specimen. Brass will behave somewhat differently than the mild steel, as it is a brittle material as compared to the ductile material of mild steel. Classic brittle behavior is a gentle curve to fracture. It does not have the same region of behavior that we saw for the mild steel specimen. It is useful for us to approximate a yield strength for the material, even though it doesn't quite exist in the same way that it did for the ductile material. We approximate this value by using the offset method. Normally a 0.2% strain is chosen, and from this point on the strain axis, a line parallel to the initial straight line portion of the stress strain diagram is drawn. This point, where the line intersects the curve, defines our yield strength. It is useful to us as engineers to measure the ductility. Any material that can be subject to large strains before it fractures is called a ductile material. As we've seen, mild steel is an example of a ductile material. Engineers prefer ductile materials for design for a number of reasons, such as their ability to absorb large amounts of energy, such as would be experienced under shock and impact. They also experience large deformations before ultimate failure. These large deformations are often visible to the occupants of a structure and thus prove early warning prior to collapse that a structure is not behaving within its design limits. There are many ways to measure ductility, two of which are shown here. We can use percent elongation, i.e. the length at fracture minus the original length, all divided by that original length. We can also use the percentage reduction in area due to necking prior to failure, which is calculated by the original area minus the area at fracture divided by that original area. Typical values are shown. A brittle material, as we will see in the lab, would have no visible necking. When a material deforms elastically, the deformations are fully recovered when unloaded. When deformed plastically, however, the plastic deformation, a part of the overall deformation, will not be recovered when the material is unloaded. Materials typically behave elastically up to their elastic limit. Even when loaded beyond the elastic limit, the elastic strains are recovered when unloaded. The property of pure elasticity is characterized by the fact that the loading and unloading of the material can be exercised an infinite number of times without any deviations from the original path. Keep in mind that in nature there are no perfectly plastic or perfectly elastic materials, but they come pretty close.